Welcome to Brain Vision.
In this problem, we have 0.055 kilograms of ice at negative 15 degrees Celsius, and we start to heat this amount of ice up by delivering energy at a rate of 800 joule per minute. And we want to find how much time it would take to, well, in part A, and at least in part A, we want to find how much time it would take before the ice starts to melt. So we can break down, the heating of the ice to two stages. One is the first stage is heating up the ice from negative 15 degrees Celsius to 0 degrees Celsius. The second stage is the melting of the ice. So in the first stage, we can apply the usual heat equation, which is Q equal to mass times the heat capacity times delta T. And we know that the mass of the ice is 0.55 kilograms. The heat capacity of ice is 2.01 times 10 to the third joule per kilogram K. And delta T is just the temperature difference between 0 degrees Celsius and the initial temperature of the ice, which is 15. So that's 15 right here. And if you plug in numbers, you're going to get 1.66 times 10 to the fourth joules. And so now we have the amount of energy that it takes to heat the ice up from negative 15 degrees Celsius to 0. So, and we know that the power delivered, which is the rate of energy supply, is 800 joules per minute, which is, we can simply take this amount of energy divided by the power, and you will get the time. So time will be 1.66 times 10 to the fourth joules divided by 800 joule per minute, and this is going to give you 20.8 minutes. So it would take roughly 21 minutes to heat this amount of ice up from negative 15 to 0. In part B, we want to find the time that it would take to melt all the ice. So melting, the heat associated with melting something has to do with the latent heat of that object. The latent heat of ice is 3.34 times 10 to the fifth joules per kilogram, and we have 0.55 kilograms of ice. Heating up the ice from negative 15 to 0 obviously doesn't change the mass of the ice. So we still have 0.055 kilograms of ice, and we simply take Q to be equal to the mass of the ice times the latent heat of the ice, and this is equal to 0.55 kilograms times 3.34 times 10 to the fifth joules per kilogram, and this amounts to 1.84 times 10 to the fifth joules. Right. And then as before, we take, let me call this time T1 and this T2. And this to be Q1 and this to be Q2. Okay, so as before, we simply take the amount of energy divided by the power to get the time, right? So it's going to be Q2 divided by P. And if you plug in numbers, you will get 230 minutes. So in total, you will need 21 minutes to heat up the ice from negative 15 to 0, and then 230 minutes to melt the ice. So the total time that would take is going to be 251 minutes to completely melt the ice starting from negative 15 degrees Celsius. And if you want to sketch the if you want to sketch the temperature against the time, then it would look something like this. Let time be represented on the horizontal axis and the temperature be represented on the vertical axis. I guess I should like that. And so we will start from negative 15. Okay. Yeah, I don't have enough space here. All right, let me draw something. This is time and this is temperature. We start from negative 15 degrees Celsius. And it takes 21 minutes to melt the ice. So this is 0. It takes 21 minutes to melt the ice. Excuse me. It takes 21 minutes to heat up the ice from negative 15 to 0. So it's going to look like this. And this is 21. And then it will take another 230 minutes to melt the ice, during which the temperature of the ice doesn't change. So the temperature will be a straight line from 21 to 251. And then after the ice is completely melted, then the temperature will start to increase above 0. So the temperature graph against time will look something like that.